Results of my master thesis, my work in Munich, and the title of the talk is EDMR on SL1 centers in silicon, where EDMR stands for electrically detected magnetoresonance. And in this talk I will in particular talk about the hyperfine interaction with 29 silicon nuclear spins. So this work was a collaboration from some people in our group, in particular Felix Höhne, my advisor, and Martin Brandt, and Leonid Vlasenko from St. Petersburg, who did the irradiation for our samples. And again, I'd like to thank Kohei for the cooperation on this work and also for having me in this group now. So I'll start with a very short outline. I will introduce the SL1 center in silicon, then move on to explain the electrically detected magnetoresonance and the effects we observe in these very samples. And after that, I will move on to the interaction with nuclear spins, where in particular I'll focus on two experiments. One is the electronuclear double resonance, and the other one is electron-stimulated echo envelope modulation. I hope you will be more clear about this at the end of the talk. So why should you actually study defects in silicon, or in particular the SL1 center? The SL1 center is a radiation defect which is created, for example, on gamma irradiation of Tucholsky-grown silicon. And these radiation-induced defects are of relevance, for example, in detectors in high-energy experiments, where, of course, high-energy phonons are common, and also in space applications, for example, on solar cells, which are used on satellites, because they also get a lot of high energy irradiation. Furthermore, defects like, for example, the NV center in diamond are nowadays get a lot of attention as possible qubits, so quantum bit applications. And by studying defects in silicon, first, silicon itself is interesting as a host system for quantum bits, because of its easy application and the high state of today's manufacturing. But also the study of a system in silicon can help us for further understanding the basic physics of triplet spin systems, which the NV center is as well, and the SL1 center is. So this can serve as a model for other defects as well. Also, as I will be talking about hyperfine interactions, these defects, they have hyperfine interactions with nuclear spins, so we can use them as probes to get knowledge about the nuclear spins, like detect them and also do manipulation, like manipulate or read out the nuclear spin state of silicon-29 atoms. So the oxygen vacancy defect, this is a silicon crystal, and as I said, in Tucholsky-grown silicon, on irradiation with high-energy photons, we create defects. Like on irradiation, vacancies are formed in the crystal structure, and since in Tucholsky-grown silicon oxygen is always present, they can form a complex with an oxygen atom and a vacancy. So there's one silicon atom missing here and one oxygen impurity, so that this complex is built on irradiation of the Tucholsky-grown silicon. This complex, the electronic structure will basically be like this, where the electrons coming from the silicon bonds are, 4 of them are paired up here in the silicon oxygen bonds, which are built here. So we get 4 electrons of the total 6. 4 electrons are mainly located in these bonds, and 2 electrons are in a silicon-silicon bond up here. So a silicon-silicon bond with 2 electrons, which can be described by 2 orbitals, one anti-binding and one binding orbital, when doing simulations with linear combination of atomic orbitals. So on illumination of a sample like this with light, you can excite this defect into an excited state where one of the electrons is lifted into the upper orbital, and now a triplet state is formed with a total spin of 1. So this the total spin of 1 this is what is called the SL1 center, this defect in a spin 1 state, the triplet state. And because this is a triplet state and the ground state is a singlet state, the transition from the s equal 1 state to the s equal 0 ground state is forbidden. And this is why we get a metastable state. So this state has a lifetime of some milliseconds. Since in a diamond lattice or a silicon lattice, there are 6 equivalent 110 directions. There are also 6 possible orientations of this defect within the lattice. And I name them 0, 90, and 60, which we'll see soon. All samples are contacted with 2 contacts, each end like nearly a centimeter apart. And the sample is illuminated on this part in between. So we have 2 big contacts on which we apply the bias voltage, and the part in between is illuminated, and we are then able to measure the photocurrent through the whole sample. And this is N-type silicon with a phosphorus concentration of about 10 to the 15th per cubic centimeter. And under illumination, in EPR, we observe a concentration of these SL1 centers, of these excited triplet states, of about 2 times 10 to the 11th. Since this is natural silicon, we have a percentage of 4.7 of silicon-29 nuclei. So these are the only silicon atoms that have a nuclear spin. The electron spin resonance of the triplet state, I'll just shortly summarize, is a Hamiltonian up here where there are 2 spin operators for the 2 electrons within the defect. So S1 and S2 are the 2 one-electron spin operators. And so the Hamiltonian consists of one term which is proportional to the magnetic field, which is the Zeeman term, and one second term which corresponds to the interaction of the 2 spins, like the spin-spin interaction, with a tensor D. The energy diagram, or the Breit-Rabi diagram, looks like this, where the energy is shown as a function of the magnetic field. So with higher magnetic fields, this system splits up into 3 triplet states, with ms minus 1, 0, and 1 being the quantum numbers. And so we can induce 2 transitions between the spin states, which is because of the selection rule. Ms has to, delta ms has to be plus minus 1 in EPR. So there are 2 allowed transitions, and for 6 orientations and 2 allowed transitions, we get 12 possible resonances for the defect, which we can observe in EPR, or as we will do now, by detection of the change in photoconductivity, which will then be EDMR. So here we show that the change in photoconductivity as a function of the magnetic field, while irradiating with continuous wave microwaves. You see that peaks are observed for the 2 central lines which correspond to the phosphorus resonance, the resonance of the phosphorus electron spin, and also for the 3 different orientations, and the 2 times because of the 2 different transitions. So a total of 12 SL1 lines and 2 phosphorus lines, which we can observe in EDMR. To further study the processes that actually lead to the change in conductivity, since it's not obvious that a change in the spin state would lead to a change in the conductivity of the sample, we can do pulsed EDMR experiments, which are experiments where just a short microwave pulse is applied of some typically like 20-30 nanoseconds. And after application of this microwave pulse, the change in the photocurrent is recorded with a very fast digitizing card. So we can see the time dependence of this process of the change of the conductivity, which can help us to further understand the actual process. So the typical transients look like this, where the different colors correspond to different line positions as shown in the other spectrum. So we observe that for all resonant lines, directly after or shortly after application of the microwave pulse, an enhancement in photocurrent is observed. So for phosphorus as well as for the SL1 peaks, an enhancement with a time constant of about 1 microsecond is observed, while on the longer time scale, as is shown down here on a higher scale for the current, we can see that the phosphorus and the black trace and the blue trace, which are the phosphorus and the SL160 orientation, the photocurrent just goes back to normal, so the delta I goes to 0. But for the SL10 and the SL190 orientation, there is a reduction in photocurrent. So this can be seen more clearly when integrating these transients and dependence of the magnetic field. So the black shaded area corresponds to the black trace here, where all peaks are observed for all SL1 orientations as well as the phosphorus, while the red shaded area for longer time constants, on this integration only the SL10 and SL190 orientation are observed. We can understand these two different processes, like the one process which is fast and which has a time constant of some microseconds and which is observed for all different SL1 orientations, and the second process which is slower and which is only present for 2 of the orientations. By first looking into literature and the process which are called slower process, the one with a time constant of about a millisecond, has been observed before and described by Leonid Vlasenko. And the basic reason for the change in conductivity is that the 3 triplet states of the SL1 have different probabilities or different relaxation rates for going back to the singlet state. As I said, the transition from the triplet to the singlet state is in general forbidden, but it can, aided by spin-orbit interactions within the defect, it can still take place. And the strength of this spin-orbit interaction now depends on the triplet state. This is why the transition to the singlet state is more probable for some triplet states and is less probable for other triplet states. So in this way, when all triplet states are created with the same probability on illumination, some will relax faster to the singlet state than others. And this way a polarization will be built up where some of the levels are occupied and others are nearly empty. And if we now induce transitions between this level, we will change the occupation of the faster recombining triplet state, and this will overall enhance the recombination of conduction band electrons and holes. So this is a process which enhances the recombination of charge carriers on resonance and therefore leads to a reduction of the photocurrent. Since there are less carrier, the photocurrent is reduced. And this was, as I said, the process corresponding to the longer time constant, while the other process was observed before but not completely explained. but was investigated in some detail in our work, which I'm not going to present completely today, but only present the basic result, which is that there's a pair process between a phosphorus donor electron and the SL1 defect. So the phosphorus donor level, as shown here with the conduction band and the valence band, within the band gap, the phosphorus donor level lies above the SL1 2 orbital levels. And so in principle, the charge transfer of an electron from the donor to the net acceptor SL1 is possible. But this charge transfer is only allowed if the spin state of the corresponding electrons is not parallel. Since in this case, with a parallel configuration, the recombining electron cannot be in this orbital because of Pauli restrictions. It can neither be in this one. So the transfer is not allowed because the Pauli principle forbids 2 electrons of the same spin in these orbitals. On the other hand, for antiparallel configurations with ms of the SL1 being -1 and being +1, and the phosphorus spin down, a recombination is allowed, as well as for a mixed configuration with ms equals 0. So when there's no Pauli blockade of this electron being transferred to the defect, this transfer can actually take place. So again, this leads to different recombination rates, a fast recombination in the allowed case and a slow recombination in the blockade case. So a lot of pairs will be in this parallel configuration because it's slowly recombining, while the orientation I called 0 and P and antiparallel will recombine very quickly. Now, we were not completely sure how this could lead to a change in the connectivity, because as I said, we observe an enhancement in the photocurrent on resonance. So we were asking, how is it possible that the recombination of this electron does not lead to a reduction because of charge carriers getting trapped and a reduction in photocurrent, but in our case it leads to an enhancement, which puzzled us quite a lot, and we have thought about this quite some time. And one model we came up with is a possible Auger relaxation process. So that after the charge transfer of the electron into the defect, there will be a negative charge state with 3 electrons in the 2 orbitals. So this might be, after the transition, an excited negative defect state. So with 2 electrons in the upper orbital and 1 electron in the lower orbital. Now if one of these electrons relaxes to the ground state, the energy of this electron relaxing to the ground state could be enough to excite the other electron to the conduction band. So this would be a defect intern Auger process, which leads to an extra electron in the conduction band, which therefore enhances the number of charge carriers and leads to an enhancement in the conductivity of the sample. So to sum up the 2 processes, one is based on the relaxation of the SL1 triplet states. So it's just the SL1 defects within the sample which have different recombination times and different carrier capture times. And on the other hand, there's a process where the SL1 defects are paired with nearby phosphorus electrons, so that the SL1s, which happen to be close to phosphorus donors, can form this spin pair, which leads to the second process, which is faster and which leads to an enhancement of the photocurrent on resonance. Now, what can we do with these 2 processes? as I said, I want to talk about the interaction with 29 silicon atoms. So this is, again, the same spectrum we've seen earlier, but now with a zoom on one of the SL1 peaks, where you can see that there are 2 satellite peaks which correspond to defects which have a strong interaction with silicon-29 nuclear spins. So this is also for all other SL1 peaks, but we just focused on one. So this means just a schematic spectrum like this. The central peak corresponding to SL1 centers, which are just surrounded by silicon-28 atoms, while one of the satellite peaks corresponds to a SL1 which has a silicon-29 spin up next to it, and one corresponds to a silicon-29 with nuclear spin down next to it. So these satellites are separated by the interaction of the SL1 electron spins with the silicon-29 nuclear spins, which are next neighbor, like placed directly with strong interaction to the SL1. So when we apply magnetic resonance, and in case of the fast process, this leads to recombination and leads to basically the destruction of the triplet state, the SL1 state. So if we apply a magnetic resonance pulse on one of these lines, then all defects corresponding to this line will not be in the SL1 state anymore. So on application of a pi pulse, microwave pi pulse, there will be throughout the sample there will be silicon-29 atoms with no SL1 next to them, but on the other hand, the silicon-29 atoms with spin down will still have the SL1 next to them, because all these defects are not hit by the microwave resonance. So basically we have a polarization of the nuclear spin states within the subspace of the SL1 state. So within all defects with SL1 state, the nuclear spin state is not equally distributed, but there are more silicon-29 with spin down next to these defects. So this means we can exploit this by a sequence like this. This is a combination of different pulses, where the blue one is microwave power, so the electron spin resonance, and the green one is irradiation with radio frequency, which corresponds to resonance frequencies of the nuclear spins. So the basic configuration, as we've seen before, is in the steady state that for both nuclear spin up and spin down, they are coupled to a SL1. Well, if we now apply a pi pulse on one of the resonances, only one of these SL1 is hit and is changed to the ground state. So basically, after application of the microwave pulse, this one is not changed, but this one is changed to ground state with the nuclear spin up. So now we can drive this polarization I was talking about by doing an RF pulse, which is resonant to nuclear spins coupled to SL1. Since the SL1 coupling, of course, changes the resonance frequency of the nuclear spins, we can apply the radio frequency pulse selectively, only on these which are coupled to SL1 or only on these which are not coupled, like coupled to something else. So we can, by applying an RF pulse with this very frequency, we can change the spin state of the nuclear spin, in this case change it from down to up, so that after illumination and recreating of the defects and re-excitation of these defects, we will get a high polarization of the silicon-29 nuclear spin, since now they are both coupled to an SL1, but only like this one was not changed and is still in spin up, while the other one was changed from down to up. So we will have a high polarization and a high number of spin up nuclear spins in the sample. And this leads to a spectrum like this, where one of the satellite peaks is enhanced because it's the number of spin up spins was enhanced, while the other one is reduced since now there are less nuclear spin down defects. I will show you some experimental data to show that we can actually achieve this. So this is the same sequence I've shown before, where the final detection is done by a so-called echo sequence, to which I will come after this, but which basically is proportional to the number of spin pairs in this configuration. So when we do a detection on this resonance, we see that the echo amplitude, so the number of pairs, as a function of the frequency of this RF pulse, is changed. So if the RF pulse actually matches the frequency of the nuclear spin, which is coupled to the SL1, then the nuclear spin is changed, and as discussed before, this resonance will be enhanced. So we see on a resonance RF pulse, the amplitude is enhanced, while for non-resonant pulses, of course, it's not changed, because the RF does not change the spin state of these nuclear spins. We can go even further, and with varying the length of these RF pulses, we can drive this nuclear spins. We can see Rabi oscillations, where the echo amplitude varies with the length of the RF pulse. So we can see we are able to coherently change the spin state of these nuclear spins in the substate. Okay, so this is one possibility to address and to observe the nuclear spins which are coupled to the SL1. But this, of course, only works when the hyperfine coupling is strong enough to separate these lines. So the spacing between these two lines has to be bigger than the broadening of the center line, because we need to address only one of these different satellite peaks. So if the spacing between this is too small, or the coupling is too small, these experiments will us not help to actually observe the coupling, which is why I come to the second technique. So this was ENDOR, or electron nuclear double resonance, and I will now talk about ESIM, which can be used for the detection of smaller hyperfine interactions. So for this, I will try to shortly explain one of the, I guess, most central pulse sequences in magnetic resonance, which is the Hahn spin echo. This is a sequence usually containing of two pulses, one pi over half pulse and one pi pulse, which in this diagram up here we have the magnetization M, which is the magnetization of the spin states. Now on application of a microwave pulse, this is rotated in the Bloch sphere. So on application of a pi half pulse, this is rotated by pi half, and the magnetization is flipped into the XY plane. So the magnetization will now be along this axis, the Y axis, and in principle for a perfect spin system, now the magnetization should just stay here and be rotating around the Z axis, because the external magnetic field is applied along the Z axis. So they should just be centered here and rotating like this. But now, because the different spin ensembles have different surroundings and have different couplings, they have slightly different Larmor frequencies. So this rotation will not be at the very same speed for all these spin ensembles. So this leads to dephasing and to a split up of the different ensembles depending on the strength of their coupling. So depending on their rotation frequency. We can, by turning this around, we can refocus this dephasing or this splitting up, because during this period, like after application of the pi pulse and during the waiting time in the XY plane, these will move with a certain frequency depending on their coupling. But now if we turn them around in the plane, so we apply a pi pulse and turn them to the other direction, they will still have the same frequency. So after being turned around, they will move back and will refocus, because during this waiting time, they'll do the exactly same movement as during this waiting time. So this period is kind of undoing the effect of the different rotation frequencies. So this is why this is called the refocusing period, where all the different spin ensembles are moving with different frequencies and are finally refocused again to one vector of magnetization, which we can then measure in our experiments. So for ESIM experiments, if we consider a nuclear spin, which is rotating in the external magnetic field, then of course this nuclear spin will have a changing influence on the electron spins around him, because it's rotating, so the actual observed magnetic field for a random spin somewhere else is oscillating. And since I said this dephasing movement has to be exactly undone in this period, this does not work if the hyperfine coupling is actually different in this period than in this period, because then this omega 1 and omega 2 will be different in this period, and so it will not be completely refocused, but will be some random results. On the other hand, if the length of these intervals, the length of the dephasing and the refocusing exactly match the oscillation frequency of the nuclear spin, then you see, as indicated by these lines, that the hyperfine interaction will still be the same during these different periods. So this leads to oscillations of the amount of refocusing. So if the oscillation frequency is hit by these spacings, then we get a high refocusing and a high signal. On the other hand, if it's not completely refocused because the hyperfine interaction is different during these two intervals, then we'll have a reduced echo signal. This is observed here. I show a zoom so you can see it's actually oscillating. So this is the echo signal as a dependence of these two intervals, the length of the dephasing and the length of the refocusing. So with longer time scales, of course this decays because the spin state is not stable forever and is decaying, but you also see a strong modulation on these states. And by doing a Fourier transform, we see that this is coupled to, this is described by, in particular, one frequency, which is the free oscillation of the silicon-29, but also other frequencies, which are the hyperfine coupling of defects and the silicon-29. So this is the interesting part where we can extract frequencies which are the coupling between these. And it was suggested that this is actually the coupling to one of the nuclear spins placed here, or there are other possibilities. We're not completely sure yet what these frequencies actually correspond to, but so the basic message is we can observe interactions that have been observed before, but can now be observed in more detail, because you can see this is a very high resolution spectrum, and we can actually observe new features of the spectrum that have not been observed in previous experience, and which might lead to a more precise identification of the actual position of this hyperfine interaction. So with this, I'd like to conclude. Summarize, we observed two different processes which we can observe separately by time domain measurements. And by using Endor techniques and EZIM techniques, we can observe hyperfine interactions of strength, of higher strength and weaker strength. And in particular, we can use this sequence to manipulate the silicon-29 spin into some spin. And with this, I would like to thank you for your attention.